Can you all hear me? Yes. All right, so today begins routing lecture 2. Starting out today in computing, 61 years ago, Jack Kirby of Texas Instruments patented the first integrated circuit, so the beginning of the computer chip. He made his out of germanium, which of course, you know, semiconductors these days are mostly made out of silicon. That was invented by Bob Noyce a little bit later. He went on to found Fairchild and then Intel. But Jack Kilby was where it started, February 6th of 1959. Today in internet history, I'm not Rickrolling you, it's Rick Astley's birthday. If you don't know what this has to do with the internet, you will not learn it in this class, but A, how, and B, lucky you. All right, so today, going to start out talking about some kinds of routing and some kinds of router, a couple ways of classifying things. Intra-domain and inter-domain routing, which we'll get the term IGP and EGP. We'll talk about internal and external routers. Then I'll talk about this notion of least cost routing. I'm going to introduce a couple of terms, trivial and static routes. Then going to go into distance vector in depth, and end up maybe doing, if we have time, a second version of the routing activity. All right. Kinds of routing, kinds of routers. So the internet does not in fact work by having one single gigantic instance of a single routing protocol. The internet is, as we have said a number of times, it's a network of networks. And the best way to route on one of those networks may not be the best way to route on another. Does anybody have an idea why that is? Why might you route differently on different networks? Yeah?
It seems like the one we used yesterday would have trouble if you had like a lot of nodes to route to. You have to keep track of so many.
Yeah, so the suggestion was the one from last time wouldn't scale too well because of how many routes you need to keep track of. Yeah, it would work fine in a smaller network, but maybe wouldn't scale to a big one. Certainly, I think you're right, especially the way we did it last time. Things will change a little bit when we talk about some tricks with addresses, instead of just having a single address for everything, like we did today, and that'll be next week. But yes, that's one. Any other thoughts on why you might route differently on different networks? Yeah? Yeah, so the sparsity of the network may be different, right? That's what you're getting at? Yeah, so, you may have networks with, a bunch of nodes and very few links, or you may have ones with some number of nodes and a very large number of links, right? You may remember you saw this data center topology last time, which was, very structured and very heavily connected. And the best way to route may change depending on that factor. Anybody have any other ideas? Well, those were two great answers. I wrote down some. The density or sparsity is in there. There are a couple things here to do with scaling. But, the high-level takeaway is that, like, different networks are different. They may be different physical sizes. They may have really different, propagation delays. They may have different bandwidths. They may have different numbers of hosts. They may have been built at very different times, right? And, things may have sort of moved on technologically. People may have had better ideas for how to route over time. Also, depending on who built the network and what for, they may have different amount of resources and different amount of investment in it, right? If you're someone like Google, you can spare some manpower and some equipment power and so on for your network because, it's very core to your business. On the other hand, if, it's something mostly used by your employees to waste time, then maybe not so much. So, there are a whole bunch of different factors that might change sort of how you route. So the sort of notion that the internet, embraces is, let individual networks choose how to route inside their own network. And we call that intra-domain routing. And then all the networks agree on how to route between those networks. And that's inter-domain routing. So to sort of sum this up, intra-domain routing more or less means routing within a single network. Technically, it's an autonomous system. I believe we will come to that term later in the semester. The protocols used inside a domain are often called IGPs, or interior gateway protocols. Gateway here is sort of a little bit of an antiquated term for router in this context. And a number of these are actively used today. There are some based on distance vector, as we've been talking about. There's some based on another type of protocol called link state, which we'll talk about next week. And then interdomain routing it's routing between networks. It's routing between these autonomous systems. This routing is sort of like the glue that binds all these separate networks into the internet. So the protocols used for interdomain routing are called EGPs, or exterior gateway protocols. And there's only one of these used at a time, ever. All the ASs agree on this, and so the internet has used this one called BGP since the mid-90s. So much of the discussion this week and next week is really very general. It's going to be true of any routing. But kind of the focus for these 2 weeks is on intra-domain routing within a particular network. And we're going to talk about BGP specifically. Later, I believe it's now going to be week 7. Sort of graphically here, here's this diagram that looks something like one that we've seen before. Where you have, these different domains that may be different things. You may have a university network, you may have, a couple different ISPs, you may have some cloud service provider. And so, these domains have their own networks, and there's links and routers connecting these domains. And so these routers all run some EGP. Today that means they run BGP. But internally, these domains have, a bunch of routers and a bunch of hosts of their own. And so inside these domains, they kind of each choose their own IGP to run, their own interior gateway routing protocol. And so you can sort of classify the routers here as being border routers, the ones that connect the domains to each other, and internal routers, the ones that are used within the domain. Is that clear? Anybody, any questions on internal, external IGP? Okay. So now I'm going to introduce this concept of least cost routing. And so last time we mentioned that we wanted good routes, right? And what was the first thing that we said, the kind of most important thing that makes a route good? Yeah?
It lets the packet get to the destination.
It lets the packet get to the destination, right? It works. That's kind of the first thing that you might look for. And so, we kind of touched on, the state for these must not have any loops, and it must not have any dead ends, both of these things. As was brought up on Piazza, there's this sort of ambiguity where De Morgan's law meets English. And so you need both of these things to be true. The second goal is that we want them in some way good, and commonly this is done by minimizing some bad value, which you might call a cost. Hence, least cost routing. So, in our activity last time, we were actually trying to minimize a cost. What were we trying to minimize? Yeah. Yeah, the number of hops it took to deliver a message, right? The number of, in this case, people in this room that it needed to go through. Each one of those was a hop, right? And so what are other things that we might choose to minimize? What might be good things to minimize on a network? I talked about some of them last time. Anybody remember or have any ideas of their own? Yeah. The latency, like the actual time to get it from the source to the destination, right? Yeah. Any other things we might want to minimize? Yeah.
Avoiding competitors.
You might want to avoid competitors. Yeah, I suppose you might be able to find a way to phrase that as a minimization problem, like the number of hops that belong to your competitor that you go through. Yeah. Any other thoughts? Yeah, so, price would be one. If there was some actual, monetary value associated with some of these links. Not all links are equally cheap. Satellite links, for example, might be very costly. They might also have very large latency. Distance, unreliability, other things. But for this class, in many cases, we don't really care. We can sort of abstract this away. And so if we have some topology like this with some routers, we can just associate a cost with each edge. In graph theory, you'd just call this a weight. And then you look to find a path with the smallest sum, right? So if you're looking for a path from R5 to R3, this one along the top has a cost of 12, so that's not it. This one has a cost of 5, so that's going to be your least cost path between R5 and R3. And so you may well have seen this before if you've taken an algorithms class or anything like that. In the routing activity, every edge, essentially, you could think of it as having a cost of 1. That gives you the hop count. If, we don't give you costs on, an exam or something, just assume that they're 1 if we don't give you any. And so you might ask, where do these costs come from, right? I mean, I just wrote them on that graph, but I mean, where do they really come from? And so generally they're going to be local to a router. A router is going to know the costs of the links that are directly attached to it. These might be something that are configured by an operator. They may actually, get into the router and configure it and tell it, this link is going to be this cost. They may be determined automatically. OSPF, which is an IGP, of a type called link state, which we'll talk about next week, uses the link bandwidth. And essentially, higher bandwidth is a smaller cost. So you could think about it like, 1 over the bandwidth would tell you, a smaller cost for a higher bandwidth. So thinking about least cost paths, they're an easy way to avoid loops, right? Because no reasonable metric is minimized by traversing a loop, right? I mean, if you had a negative metric, then yes. But if you had a negative metric on a loop, then actually you minimize it by staying in the loop forever, right? So, no reasonable metric for networks is negative like that usually. Least cost routes are also destination based, right? All you need to know to follow a least cost path is the destination. And they form a spanning tree, which implies that they have no loops. But we sort of looked at this concept of these delivery trees that were related to spanning trees last time. So a terminology note here. When I say shortest path, I mean least cost path. When the weights are 1, these are the same thing. They're just a hop count. But the text uses shortest path specifically to mean based on the hop count, and it uses least cost path when it's talking about edge weights. I think this is actually kind of unusual, but that's what the text does. Any questions on least cost routing? All right, moving on. So trivial and static routes. So there's a couple kind of routes which are uninteresting, and you probably get them kind of for free, and therefore I will often ignore them. But I want to mention what they are. I'm going to call them trivial routes, which is not a standard term, but it's how I'm going to classify them together. And so the first one of these is a route to yourself, with a cost of 0. There's, no better way to get to yourself than yourself. So in some contexts, these are called loopback routes, but don't feel a need to remember that. But if you ever read that because you are a masochist and reading Cisco documentation, that's what this refers to. In lots of scenarios, these don't even end up in routing or forwarding tables. It's just sort of assumed that these exist, that you can reach yourself. The second one I mentioned last time, and it's a default route. And it makes sense, especially in a case like A, B, and C here, where each of them only has one link. If any of them have a packet that isn't to themselves, then the one possibility is your one neighbor. You don't need a detailed routing table to know that the only way that you might possibly reach your destination is using your one hop. Does that make sense? So you sort of just have this wildcard entry, like here, like if the destination is anything, then the next hop is going to be R1 at some cost. In fact, you often also just have, even if you have multiple links, you probably have a default route because you're probably going to prefer some links to others. For example, your cell phone may have a link, a virtual link, a wireless link between your phone and your cellular network and your phone and some Wi-Fi network. And you probably want to have a default route for the Wi-Fi network, right? Because it's probably going to be less costly for you. Any questions on trivial routes? Okay, so the other one is static routes, and this is a standard term. And so static routes are manually entered by an operator. So why would you do this? Why would an operator want to manually enter a route? We're talking about these routing protocols that are supposed to, populate routing tables for us. Why would an operator do it manually? Yeah.
Maybe there's a route that's likely to stay up for a long time.
So maybe it's a route that's likely to stay up for a long time, yeah, and you don't need to have some dynamic protocol to figure it out. Sure.
Could it be like sensor, like a monitoring reason?
A monitoring reason? Could you say a little more?
Like censorship.
Oh, a censorship thing. Well, you certainly might want to direct some traffic a certain way so that you could monitor it, like get it out of its normal path so that you can do it. So an operator might want to sort of override for one reason or another. They might want to kind of override what the routing protocol would do, right? The operator may just be like, I know best, or I know what I want to do. So they're going to use this static route to kind of override it. Does that kind of fit with what you're thinking? Yeah. Any other thoughts? Yeah. You might want to keep packets from going over a competitor's network. Yeah, sure. Again, this sort of falls in this category of, the operator may know best. You would hope that your routing protocol would actually be flexible enough to let you, configure it so that it would do that for you, for example, by changing the weights on some path. But sure, that same idea of, operator may know best. Yeah. you may know what path you want to take. Yeah. Maybe for debugging, you may want to do it. So yeah, I think these are all kind of falling into this same sort of general category of, the operator may have something very specific in mind that they're trying to accomplish. And so that's certainly one reason. Sometimes the operator just knows what they want. Maybe more importantly is that, I mentioned last time that hosts generally don't participate in routing protocols. So how would a router even know where the hosts are to begin with? And the answer is that an operator actually on the router adjacent to hosts specifically enters a route that tells it that that host is there on that particular link. So like for R1 here, an operator would have entered static routes for A and C. And so you can sort of see, A and C have these static routes saying C is out port 0 here. If it ever matters, we'll note that they're static somehow. And I've shown it here using the port number style of table that we looked at last time. Like I mentioned, we usually won't show them like that, so we'll show them something like this when we're using the neighbor name. We'll just use the neighbor name as the next hop. So the same thing as the destination. Or we'll say direct. And so you might not believe me at this point that, like some operator somewhere has actually entered your phone's or your laptop's address on every network that you've ever connected it to. But as the semester goes on, we'll talk a little bit more about how IP addresses work, and we'll talk about this protocol called DHCP, and it should become more believable. Any questions on these? Yeah. Say this again. I may have missed the first part. Well, so I guess trying to draw a parallel to the routing activity, right? When you were sitting next to someone, in some sense, maybe you knew that there was a router adjacent to you because they at some point tried to give you their number, right? They said, the person next to you said, "I'm offering you number 45," right? And so that's the routing protocol. That was them offering you that thing. And so if they're a host and they don't participate in the routing protocol, how would you know they were there? I mean, they're a person, so you just look next to you, but, conceptually. So there isn't, with routers, there's this protocol that they're communicating in, which lets them, sort of say hello to each other and know that they're there in some sense. But hosts don't do that. Does that make sense? Any other questions on this stuff? Okay. So now let's talk about distance vector routing protocols. As I mentioned last time, they've got this long history on the internet and on its predecessor, ARPANET, and a bunch of other early networks, going back at least as far back as 1969. The sort of prototypical distance vector protocol is RIP, the Routing Information Protocol, which was written here at Berkeley. And so our discussion of distance vector is pretty similar to RIP in a lot of ways. It's got this strong relationship to the Bellman-Ford shortest path algorithm. And our in-class exercise was basically a version of Bellman-Ford. It's sort of halfway between Bellman-Ford as you would find it in a textbook and a shortest actual useful routing algorithm, routing protocol. And so today we're going to talk about it some more, and we'll get much closer to being a useful routing protocol. The text has a much more sort of formal and algorithmic write-up of distance vector. You are welcome to read it. You're welcome to talk about it with people in office hours. But what I'm going to try to do in this lecture is give you sort of a more procedural sense of how it actually works as a routing protocol in practice. It gets a little bit tricky, so please stop me, ask questions. Be aware that your first project is on this subject. So I want to start by sort of refreshing your memory of the activity. And I'm going to propose some small changes. And so basically, I was having you all pretend to be routers. You all had links to your neighbors. And we were routing to Ian, one of our TAs. And so a major part of what you did was remember your distance from Ian along the best path as far as you knew. And you didn't know it was your distance to Ian at the time because I call it a magic number. But that's what it was. And when we started, you all had infinity as your distance because you didn't know about any path at all. I also asked you to remember who gave you your number, but I told you not to worry too much about it because we could figure it out easily later, and I didn't want to burden you with remembering two things. But that person who gave you that number, which we called your best friend, of course, that was the next hop on the way to Ian. But especially if you'd written it down, right? You could have kept track of this too. You didn't need to figure it out after the fact, right? You could have kept track of both the distance and the next hop at the same time, right? Right. I'll take that as assent. So when you changed your mind about your distance, right? When you got a new number, you immediately told your neighbors, right? Because it might change their mind about what their best distance is. And you added the additional hop when you offered them the number, right? I had you take your number, add one, and offer it to the person next to you. But you could have just told them your distance and had the neighbor add the one, right? Like that's equivalent. Which one of you does it, right? I did it the way I did it because this way you only had one person doing the addition and the other person doing the comparison. I thought that would be easier, doing one operation per person instead of both. But I think you would agree that, especially if you're writing a program, you could certainly do these both at the destination side. You added one every time you did it, right? One more hop. But you could have added some arbitrary other number, right? You could have said, we could have had a rule like, well, if the neighbor that you're handing it to is wearing blue and gold, then the cost is 1. If they are not, then the cost is 2, right? And then we'd have paths that optimized for people with Berkeley spirit. You could have taken the number and added your age to it. And then we would have been finding paths with the least, average age, right? You could have added any number besides just one, and you could have added a different number for different neighbors, right? And finally, you could have done this for multiple destinations, right? I didn't want to have you keep track of an Ian number and a Shreya number and a Vasu number and whatever. So I just, had you do one. But you could have, right? Especially if you were writing them down. That would have worked, right? You could completely independently say, I offer you the Ian distance of 7 and the Raphael distance of 10, right? Everybody good with this? All right. So a quick aside now. I wanted to sort of relate what we were doing to something, some concepts that we covered last time. And so last time I had this slide that looked very much like this at one point, and was comparing routing and forwarding. And it said, routing, communicate with other routers to determine how to populate tables for forwarding. And forwarding looks up packet's destination and table and sends packet to given neighbor. So figuring out your best friend by sharing magic numbers was routing, right? That was building routing state. Your number, your magic number, was your routing state. It was the distance to the destination. So what was forwarding? In the exercise. Yeah.
Referencing your magic number.
It was referencing your magic number. Sure, that's true. Do you have a different answer?
It was giving the envelope to the neighbor.
Yeah, it was giving the envelope to the neighbor. It was passing that envelope, right? I mean, when you passed the envelope, you were referencing that state to figure out who to pass it to, right? But you got an envelope, some of you anyway, and you thought, who's my next hop? And you passed the envelope to them. What's a packet? The envelope, right? The envelope was the packet. So that's forwarding, right? Forwarding is the one that actually got the data, the message, to the destination. That's what forwarding was. The way you figured out how to do the forwarding, that's what routing was. Is that clear? I know the two concepts can be a little bit muddled at first, but hopefully, having done it physically, I hope that connects. All right. So I wanted to compare compare the normal serial Bellman-Ford algorithm that you'd see if you looked it up in an algorithms text with what we were doing in class. So the serial Bellman-Ford algorithm is something like this, unless I misremembered, wrote a bug. But I think it's pretty much that. Don't worry about trying to understand immediately everything that it does, but we can see some things that we recognize. The magic number and the best friend, right? The distance and the next hop. It's keeping track of these things. We started with infinity, right? Except for the destination, Ian, who started with 0, right? These are sort of the setup, the initial conditions. And you can see where it compared an offer to a current value, right? It looked to see is, some distance, from my neighbor is my neighbor's number, plus the distance to my neighbor, smaller than the distance that I currently have now. I'm distance R2. If that's true, then you accept the offer. You change your distance to be the distance of your neighbor to the destination, plus the distance from you to the neighbor, right? And then you remember your best friend, right? You remember your next hop. But we were doing this in parallel, right? Like, nobody iterated over all of the links. No one person iterated over all of the links when we were doing this experiment, right? You only ever iterated over, the links that were directly attached to you, right? Your immediate neighbors. Together, all the links got iterated over. But no one person did it, right? As in the serial version of this algorithm. And we did it asynchronously, right? Like everything here, looking at your neighbors and comparing the distances, each one of you was doing that individually, asynchronously, right? You weren't all being like, okay, everybody, it's time to exchange your numbers with your neighbors. It's time to compare. It's time to exchange your numbers with your neighbors, right? We weren't doing it in this lockstep sequence like the serial version of the code here. You were all doing it at different times and probably at different rates. You probably did different numbers of this. You were doing it, completely asynchronously with everyone else and in parallel with everybody else. And then there's this thing. What is this thing? This thing wasn't really in the version that we did at all. This is this termination condition for this thing. So, the basic idea with this thing is that if you do the inner part synchronously, then the most steps it could ever take to get the answer is the person with 0 tells their neighbors 1, who tells their neighbors 2, who tells their neighbors 3, right? And this is going to stop when you run out of neighbors, right? So the maximum number of steps this could possibly take is the total number of routers, right? So that's what this kind of termination condition is. But we didn't have that at all. It doesn't make sense if you're doing it asynchronously, right? Because you're doing perhaps different numbers of these updates. But fortunately, it doesn't matter. The version that we did self-terminated, or at least it could self-terminate. Eventually everyone got, or should have gotten, like the lowest possible number, at which point you wouldn't have anything to tell your neighbor, right? Nobody would ever give you a better number eventually because you are actually some distance away from Ian, right? Like eventually you'd find the right answer. You have nothing else to say to your neighbors. So eventually this stops, everyone goes quiet, and we reach this new stable state that's correct and actually, represents the state of the world. We call this being converged. And getting there is, converging on good routing state. And finally, just to drive this home, a difference from the serial version algorithm, the inputs to this are all the routers and all the links. And the outputs are all the distances and all the next hops. But that's not what we had at all, right? No single person here knew the whole topology, knew who all the routers were, or even how many routers there were, or who people were sitting next to. All you ever knew was this local information about who was directly around you, and all you knew at the end was, your distance to Ian, not everybody's distance to Ian. So at least this worked for most people. I think we had some partitions. I think we had some malicious actors, but at least in theory, that's how this works, right? And so my point with all that is that, as a group, we did implement something very close to this serial algorithm, but everyone executed parts of it using parts of the input and learned parts of the output. Does that make sense, the sort of relationship between what we did and Bellman-Ford, the serial version of Bellman-Ford? So there was this great question after last class. Why not use Dijkstra's algorithm instead? Isn't it faster? So is it faster? I mean, the big O, usually, right? It's got this additive part. Even if it was E plus V, right, as opposed to E times V, right? That's going to be worse, generally speaking. But what's not fair about this? This is not an apples-to-apples comparison. Why is this not an apples-to-apples comparison? Yeah? Yeah, so that's a big part of it. That's a good observation that, Dijkstra's assumes you know everything ahead of time, right? And we didn't in ours. In fact, we never knew everything, right? And sort of, on that same sort of note, what we were implementing was this parallel distributed asynchronous version. Is it possible to do that with Dijkstra's? Is it efficient to do that with Dijkstra's? The big O, of the serial version doesn't necessarily apply to a parallel version. We will later, next class, talk about an IGP routing protocol that uses Dijkstra's algorithm, and it does not do it by making it parallel and distributed and asynchronous. Anyway, it's just not sort of an apples-to-apples comparison here. Does that make sense? Yeah.
Also, that Dijkstra's just calculates for one pair, a source and a destination.
Dijkstra's can come up with all pairs, all sources to one destination, or all destinations to one source. It can do that. Yeah. So there are variations of Dijkstra that do what you're saying, or at least don't get all of the ones, but it can. Okay. Moving on. A final point is that with distributed algorithms, the performance killer is often not the computational complexity, it's the communication. And what we did on Tuesday, you kept having to tell your neighbors essentially this quantity I've highlighted in blue here. You keep having to communicate that, but that's kind of the only thing you need to communicate. Different algorithms, like maybe if you tried to parallelize Dijkstra, you might find that you need to communicate other things, or you might need to communicate more often. So it's often, the computational complexity of some of these things, there's an addition operator and a comparison in there. These are things your CPU can do very fast. Quickly, network time will probably dominate this. Okay, so in a second, I'm going to get to some examples where we look at the behavior of the full network. But first, I want to make sure that you're really comfortable with the basic table update process. And so before even that, I want to make sure that, to point out, that this table can be used for forwarding too, right? So the way we've set it up here is there's a destination and there's a next hop, which looked like the tables that we looked at last time. But now there's also this distance in there, right? But you can certainly just use the next hop to do forwarding. I mean, you did it with the envelopes. And so now, thinking about how we do updates of this table. If you had this table and the person to your left told you that they could reach Ian in 7 hops, we'd say that they advertised a route to Ian with a distance of 7. And you think, well, all right, if they can do it in 7, I can do it in 8. That's my neighbor's distance to Ian plus my distance to my neighbor. And so you would cross out your old entry and write in this new one. Use the person to my left, and it'll be a cost of 8. Make sense? Thumbs up? All right. Now, if the person in front of you tells you, I can reach Raphael in 3, you might say, what? Who? And what you do is you add another row to your table. It says, all right, well, using the person in front of me, I can reach Raphael in 4. And you can just sort of keep processing updates or advertisements like this from your neighbors. And you end up populating this table, and, it looks like for Shreya here, somebody told you 16, then somebody told you 13, and now somebody told you 12, right? So you just kind of keep updating this every time you get a message. Yeah? For the versions that we're doing right now, in this context, yes. Because we don't have any way of, we could think of having some sort of aggregate route. You could say all the names of people starting with the letter A, all the people starting with B, that sort of thing. We're not there yet, but yes. Yeah? Pretty much, potentially, yes. Kind of when you did it doing the activity, it was like when somebody told you something that changed what you would say, you said it, right? So, if people send you something and it doesn't change your mind, then you don't do anything. If it does, then you do. And we'll come back to that specific question in a minute. All right, so now let's walk through some examples, starting with this really simple one, and as we do later ones, we'll run into some problems, and we'll see what we can do about them. Okay, so right now, there's nothing for this routing protocol to do, right? Unlike the exercise, we don't even have routes with the cost of infinity here, right? Like, we don't have any routes at all. So what needs to happen? Yeah?
We need a destination.
You need a destination. How does the destination get entered into the system? So what are the destinations? Yeah. Hosts, right? And so why are there no host routes in any of these tables? There's a host, right? A is here. Why is there no route for A? Yeah. Hosts don't participate in routing. So how did we fix that? Put it in manually, right? A static route. So what's the static route look like here? Which router is it on? Everybody say it. It's It's on R1. And so what's the destination column of this table going to be? I heard someone say it. It's A, right? We're talking about A. And it's this direct route to our neighbor, and we'll say it's a cost of 1. So, our operator decided she thought it was a cost of 1 and put that in there. It doesn't actually matter what cost our operator decides to put in, does it? Why does it not matter what cost the operator puts in here? Yeah? It's the only way to get there, right? They put in 1 and a path would be 10. They put in 100 and the path would be 110. It doesn't make any difference. The only way to compare it is by adding that number anyway. All right, so what happens next? What did you do in the yeah? You got to tell R2 that you've got this route, right? So we're going to make a packet to send to R2 to tell them something. And so R1 is going to advertise this route to its neighbors. And we're going to write down the source of this route advertisement. We'll do it on the left side of this packet here. So this is a route coming from R1, so we put R1 in the packet here. Might be in like the source address field. And on the right side, we're going to put the destination that the route is referring to and the cost. Right? So notice that we don't put the next hop in the packet, right? Because what's R2 going to do with it? It's R1's next hop. It's not R2's next hop, right? Not necessarily useful information for R2 to know. Does that make sense? Yeah. All right, so it's going to send that packet to R2. R2 looks at it and says, this is a route for the destination A. It doesn't have a row for A. What's it do? Creates one, right? And so now it's got to figure out what the next hop and the cost is. So what's the next hop? R1. And what's the cost? 2, right? It's 1 from the packet and then 1 for that link that it came in on. So now the world looks like this, and now what happens? Yeah?
R2 tells R3.
R2 tells R3. But something else, I think, which is sort of interesting, happens. There's this question, is this what you would have done? Would you have sent it to both R2, or rather to both R1 and R3? And I doubt it. You apparently would not have. I bet a lot of you didn't. Thumbs up. Would you have sent the one to R1 or not? I see a lot of thumbs down. So I think that's really interesting. And I'll come back to it in a minute. I'll point out that I definitely said to do it in the instructions that I gave you. I said send it to all your neighbors. So I think this is interesting. We'll come back to it. But all right, if you violated my directions and didn't send this advertisement to R1 or wouldn't have, then good for you. It took the early networking community 5 years to decide not to do that. And a lot of you seem to have done it intuitively on your first try without knowing what you were doing. So, interesting. All right, so pretending you actually follow my directions, R1 would have gotten this advertisement here, right? And we see there's an advertisement for A, which we have in our table. And if we use this advertisement, what would the cost be? What's the cost being advertised? Just say it. 2. And so what would the cost be if R1 used it? 3, right? That's worse than the current route. So we would ignore it, right? And this other one on the right, what's the destination? A. And what's the next hop? R2. And what's the cost? 3. And so we fill that in, right? And so now what happens? Are we done? Yeah, so if we followed my directions to the letter, R3 is going to send it back, right? And it's worse than the current route at R2, and so it's going to get ignored. And now we've converged. Now we're done, right? Now there's nothing else to do. Everybody's got a table entry that reflects reality. Their table hasn't changed, and so we're done. Any questions on this example? Yeah?
When you actually do this with R2, have R1 and R3 as destination in the sorting table, that's how it gets.
So for IP routing, it doesn't necessarily need to. It will have them in their forwarding table. It gets into this bit of complexity with the layering. But in many cases for IP routing, you would have destinations for all the other routers. Any other questions? Yeah? How does it work within? When a router goes down. Yeah, we'll come back to that. Another question? About adding new things. Okay. So before we get to that, we will come back to this momentarily. What about multiple hosts? And I hope you've gotten this by now, but I just want to really drive home how this works with multiple hosts, right? So here's a version of those topology. We've added a new host. We've added B. There is a static route that's been added for B at its adjacent router at R3, right? And so at some point in time, R3 would be sending these advertisements to its neighbor, right? Doesn't really matter when. These two things can happen, asynchronously. At the same time, they're completely independent. The routing for A, the routing for B. They follow the same process, but with different rows in the tables. Does that make sense? Do you believe that this thing just kind of trivially scales to hold multiple things? And therefore, we can sort of ignore multiple hosts for many of these examples because it makes things a lot easier. All right. I want to talk about this exception to the rule. So thinking about our logic for when we update our table. If we get a route and we don't have a destination in the table at all, we should add it, right? That's sort of one condition that we have. And another one, the big one. What's the big one that we have? What's the big condition for when we update the table? We've said it a bunch of times. Yeah? The cost of the new one would be less than the cost of the current one, right? So there it is. If the current route distance is greater than the advertised distance plus the distance to that neighbor, you replace the current one, right? So here is a routing update from R11 for cost 9. Are you going to update the one in R8 here? Thumbs up if you're going to replace it. Thumbs down if you're not going to replace it. Thumbs down, right? We're not going to replace it. This one's worse, right? The one that's there is 6. This one is 9. You add 1, it's going to be 10. That's worse. All right. How about this route from R5 with the same cost? Cost 9. You're going to replace the one that's in there? Thumbs up, replace it. Thumbs down, don't replace it. I see a little bit of a mix. Anybody want to argue one way or the other? Yeah?
Because this particular packet is coming from the router that originally had the lowest cost, something may have changed down the road.
Yes.
I might have to update it.
Something may have changed down the road, to the left of R5 here, right? I think one way to think about this is What is the only reason that you know about this particular route at all? How do you know about this route? Where did it come from? It came from R5. And R5 at some point told you 6 or told you 5, right? Now R5 is telling you 9. Have you, between then and now, decided that you don't trust it? Right? I mean, the only reason you know anything about it is because it told you. It's telling you something different now. It's right. Does that make sense? Yeah.
What if in the meantime we got a better number? So that choosing this 9 works.
Well, so it's you're like the one in the table is this one, right?
Yeah. Well, like what if the one we got from R11 was 8?
If you got 8 from R11,
Yeah.
so that's right. So I think you're getting at something here, which is, this one that's R9, you should accept it. You should just trust it, right? Because so here's the other condition, right? If the advertiser is the current next hop, right, then replace the current one. So that's the condition you need to think about, right? Like if your next hop, the route you're using, is from that same router, then you want to update it. But so here we get to this thing. If it told you 12, right, you should update your cost to 13. Because if that R11 sends you this 9 again, you want to choose that 9. So before you can choose that 9, you have to choose that 13, right? Like if you'd left your routing table at 6, then when you got that 9, the 9's worse. You're not going to pick it. But R5 is also telling you 12. And so if you take the 12, now all of a sudden the 9's better. Does that kind of get at what you were getting at? Yeah. So I see what you're saying, and I think we're going to come back to this a little bit, but I mean, you're saying it may matter what order you get them in. Though I would say, you're always, yes. So I get what your point is there. It kind of matters what order you get them in. You're absolutely right. We're going to come back to that in just a couple slides. Yeah. Say this again.
So if R11 still has a route cost of 9,
Yeah.
Is there any guarantees that R11 will eventually send that to R8 after it accepted 13?
Yeah, and so I think that's the same question of like the ordering matters, and so let's come back to this in just a moment. Yeah.
I just wanted to say a word around the R11C to R8 saying that they can get to after 12 and they can do better than the hell that R8 is back. Like just this the R8 that they said after it's not.
Say this again.
So after R8 updates distance to after 12, it tells R11 probably could be better.
Yes, so you're saying you could have some version of this protocol, if I'm understanding what you're saying, where when F updated and went to 13, it might tell R11 something, and then R11 might say something back. Is that what you're getting at?
Yeah.
Yeah, okay. So, yes, there are ways you could work around this problem of the ordering mattering. Agreed. We'll come to a really simple version. Yeah.
Is there any reason you could just store an integer and store a min something instead? Is there any reason you just need to store an integer? Could you store like a min heap for instead?
So instead of just storing the one, you'd store like a bunch of different, of the possibilities, right? And then you're saying when you lose one, you could maybe just pick the next best one. Yeah, so you can do that. It's a slightly different version of the algorithm. The version we're going to implement doesn't do that. One of the things that you find is that many of your neighbors, often downstream, are using the same path anyway. So when one of them's wrong, it ends up that they're both wrong. But yes, that's a possibility. The idea was, you could keep track of, the advertisements from a bunch of your neighbors and then just sort of always pick the best one. But we'll get to a very simple mechanism for doing this, which is this. It's pitched a slightly different way. It's asking the question of, is this reliable? We're sending these distances between neighbors, but our networks are only best effort, right? So those distances could be dropped. And sort of equivalent, the distance being dropped could be they come in the order that you don't want, right? There's a relationship between these things where you sort of missed the one you want. Do you get a chance to fix it later, right? And so, like earlier, we saw R1 create and send this advertisement to R2, but what if, this packet doesn't get there? This packet gets dropped. Something bad happens to it. So from what we've described so far, as I think we've been coming up with, we don't really have a way to deal with this. So does anybody have a really simple idea of how you could fix this problem if this routing update got dropped? You might think about, if you were doing this in the activity, the equivalent of a packet being dropped would be if, your neighbor didn't hear you. How do you fix this? Yeah. Retransmit, right? So, if you just drop one packet, a super simple thing you could do is just resend your announcements every so many seconds. And we call that so many seconds the advertisement interval. This should work eventually, right? Assuming the link is working and it's kind of just dropping a packet here and there, right? If you just sort of keep telling your neighbors, then this will go through. And similarly, this solves the problem of ordering, right? Because, if you get if it sends the 9 and you don't take it, but then you get the 12, and then it's like, oh, now the 9 would look good. Later, the 9 will come again if our 11 had just been sort of retransmitting. So, what you did on Tuesday was what we'd call triggered updates, right? When you got something that changed your number, you told your neighbors, right? It was this sort of reactive triggered effect. You got this event, and it triggered your reaction. But we can also do this sort of timer-based one. And so for the sake of examples here, we'll do every 10 seconds, we'll say, we're going to retransmit. And so sort of comparing, this sort of timed interval one to these triggered updates, right? Like, the timed interval should always work, right? It gets you reliability. On the other hand, if you're only doing it every 10 seconds or every, in the case of RIP, it's every 60 seconds. So, it's not as timely, right? Between updates. You may get an update and wait another 60 seconds before you tell somebody. So one gets you reliability, and one gets you, speed. Does that make sense? Why you have both of these two things? A final note here is that, the timers, when they retransmit their advertisements, they're not synchronized, right? Like, every router is potentially doing it, offset from the other ones. So because of, the timers being offset and because of packets being dropped, advertisements can sort of come in unexpected orders. And so in the following examples, I'll show you some things which can happen. It doesn't mean that they're always going to happen. It depends on, the ordering of a bunch of these things. And in particular, I'm going to not show triggered updates a lot just because it makes things hard to reason about. So a minute ago I mentioned that I thought something interesting happened, and I want to investigate that. So it goes something like this. R3 gets an advertisement from R2 and adds it to its table. And if R3 is advertising all its routes to all its neighbors, then it'll send one back like this, which R2 is going to ignore because it's worse than the existing one. And a lot of you said that you didn't do this. And so why not? Why did you not do this? Why did it not even kind of occur to you to do this? You must have had a reason, right? Yeah.
Is the packet that was sent to us that had us update our table entry came from that direction?
Yeah, so it's back in the same direction, right? Like the next hop would have been the one that gave it to you, right? So, there's sort of no point, right? The route that R3 is advertising is the same one that R2 gave it in some sense, right? It's like R2 gave it and then R3 is trying to give it back. It couldn't possibly be on the shortest path. R3 could not possibly be on the shortest path between R2 and R1, considering R2 gave it the route. So aside from being pointless, that can be problematic. And this is a contrived example for the sake of simplicity here. But this can happen other ways. I'm just trying to make the point. So imagine there's a momentary power outage and R1 and R2 reboot. They come back and their tables are empty. What's the next thing that happens? Somebody's going to send an update. Who's going to send an update?
R3.
R3 is going to send an update. And this is what it's going to be, right? It's going to accept that because it didn't have a route at all. And the next thing that's going to happen is R2 is going to send an update. It's going to go to R1, right? And what's up with our table entries right now? Are they going to forward the packet to A? They're going to forward it the opposite direction of A, right? They're totally backwards. So that's not so good. So the sort of takeaway here is, why would you advertise a path back to the person who advertised it to you? Telling them about your entry going through them, doesn't tell them anything new. And it can mislead them into thinking that you've got this independent path, which you don't actually have. So the solution is, if you're using a next hop's path for some destination, don't advertise that destination to that next hop. Advertise to everybody else, but not back to them. And so we call this split horizon. Does that make sense? See a couple nods. All right, so going back a second, I want to look at another problem. And, again, this is sort of a contrived example, but this does happen other ways. So let's pretend that we didn't implement split horizon here. And we'll ignore R1 for the moment because it's not that interesting. So R3 sent the update to R2, and that changed R2's table entry, right? It didn't have one before, now it has one. So it's going to send an update back to R3, right? With this cost, its current cost of 4, right? So would R3 accept this advertisement? We got a no. Anybody else? Would it accept it? I see a yes. Why would it accept it? Yeah.
It would, because R3 has its records that R2 was where it originally got the record from.
Yeah, right? So this is a special case, right? Our current next hop is R2. This advertisement is from R2, so we always accept it, right? This is the special case. So it's going to update its entry to 5. And so later it's going to send an advertisement. What's that advertisement going to be? It's going to send this update for a cost of 5. And that should say 6, but it says 7. But it's going to update it to something, 6 or 7, somewhere in there. And, that's going to then advertise it back. It's going to say, oh, well, that's worse. Or it's from the right neighbor, so now mine is going to be 8. And so this is never going to converge, right? These are just going to keep toggling back and forth with each other. Each one saying, oh, well, you told me 6, so mine is going to be 7. So I'll tell you 7. And you say, okay, well, then mine's going to be 8. And so it just goes back and forth forever. And so we call this counting to infinity, the counting to infinity problem. And again, this particular instance of the counting to infinity problem is solved by implementing split horizon. But there are cases, you will see one in the project, I think you will see one in discussion, where it doesn't solve it. But does anybody have an idea of what to do about it? The accepted solution is very simple. Yeah? well, that's split horizon, right? Just don't send it back ever. That would be split horizon, which I admit does solve it for this case, but it doesn't solve it for all cases. So how could you make sure that to solve this problem so that it's going to converge to something always? How could you stop it from counting? Yeah.
We have R2 also say where it got the
Interesting. You could have R2 also say where it got it from, and you could sort of detect the loop, right? It's an interesting idea. We will come back to that later. Not today, but next week probably. Good idea. But even simpler than that. So pick some maximum value, and when you reach that, just stop. So rip, when it gets to 16, it's like, all right, 16, it's unreachable. Just stops. So 16 is effectively infinite for rip. And so then you get to 16 and you stop. It doesn't update your table anymore. You say, oh, okay. And then you converge, right? And so you don't think, in this case, you'd say, okay, A becomes infinity, A is unreachable, which of course, it was in this example. So now we come to this question that we got, can this handle new links? This question was asked from up there. And so, we said we want to adapt to changes in topology. So what if we add a new link? So imagine we've converged on this topology like we've had before, and we add this new link. What's going to happen? Is anything ever going to happen? There's these periodic updates, right? So at some point, R1 is going to send an advertisement, and it's going to be better than the current route that's in this table, and so it gets updated. And so when you add a link, it pretty much just works, right? So we're going to skip the break, and we're going to ask this question: can it handle failed links? And so let's go back to this topology with the extra link, but this time it's going to have this cost of 4. So this network is going to originally converge to the same routes as before because, R3 is getting advertisements on the top link, but they're worse than the routes that it's getting from R2, so it's ignoring them, right? And now we're going to say that this link between R1 and R2 fails completely. No packets are ever going to make it across this link again. But there's still connectivity between every node in this topology, right? But the paths from R2 and R3 don't work. So, what can we do to detect and handle this failure? And I'll give you a second to think about it, but remember first that R2 had been getting an advertisement from R1 every 10 seconds, right? It had been getting those periodic updates, and now it's not. So how can we deal with this? Yeah?
R2, once it figures out that it's not getting any more updates, you could send out a packet saying, put the max infinity, on its R lines.
Yeah. So you're skipping ahead a little bit here, but you've definitely got the right idea. And so the idea is that, we can add sort of another field to this table, a time to live. And basically say a given route only lives for a certain amount of time, right? And so that number, when you get the route, it just sort of counts down. But every time you get an advertisement for the same route, you just charge it back up, right? So every time a neighbor advertises it to you, maybe you say that it's 21 seconds. So you get a route and you say, this is valid for 21 seconds. Your neighbor is advertising every 10 seconds, right? So even if it misses one, it's going to keep it alive. If it misses 2 in a row, well, now that one's going to time out, right? And so how this works, it gets the advertisement, it fills it in with this time to live of 21 seconds. It's going to advertise it. R2 is going to advertise it to R3. We'll say that, the first advertisement happened at T0. And so, R1 is advertising, every 10 seconds, 0, 10, 20, 30. R2 is going to advertise offset by 5, so 5, 15, 25, so on. And so at time equals 5, it's going to send an advertisement to R3. And so at that point, the time to live for the original route in R2 is only 16 seconds. And the route from R2 is better than R3's current route, so it's going to replace that and set the TTL to 21 seconds. And so R3 is now going to be advertising to R1 and R2 also, but for now, those routes are always going to be worse, so we're going to ignore those. Is everybody sort of clear on what's happened so far? We've just sort of copied these in, but now these routes have this time to live from when they originally got it. Does that make sense? They're just counting down. So 5 seconds later, at time 10, R1 sends its periodic advertisement again, and R3 ignores it because it's worse. So I'm going to hide that. But looking at R2, R2's route has a TTL of 11 seconds because it got it 10 seconds ago, right? 21 minus 10. But R2 looks at this new advertisement and says, yeah, this is the route I'm using, right? It's got the same route through R1 with a cost of 1. And so it's obviously still alive. And so it's going to bump the TTL back up to 21, right? So it's keeping that route alive from these periodic advertisements. So now let's say, right at this moment, immediately after R2 processed this advertisement, that's when the link fails. This route is now worthless, but nobody knows it yet. So 5 seconds later, R2 advertises to R3 again. R3's route gets recharged, so now it's got 21 seconds again. 5 seconds after that, R1 sends its update again. R3 ignores it again. But the one to R2 is never going to get there, right? Because this link is down. So R2's route doesn't get recharged. It's just going to keep counting down. 5 seconds later, the TTL on R2 is now only 6 seconds. R2 is going to recharge the route on R3. 5 seconds later, R1 sends routes again. It's the same as last time. But now notice that R2's route is almost dead, right? It hasn't gotten an update now for 20 seconds. So 1 second later, this route expires. And you clean it out of the table. So 15 seconds later, what happens? Yeah. Yeah, the time to live right now is 15 seconds in R3. So 15 seconds later, it's not getting any more updates from R2, so that one gets cleaned out. So following that, at t equals 50, again, R1's timer goes off. It sends its advertisements. R2 doesn't get it, but R3 gets one. And this time it accepts it, right? Because it had no entry at all. And so it fills it in R3. And we've been ignoring R3's updates because they weren't interesting until now. But now, at some point, we'll say at t equals 52, R3 sends an update, and it gets to R2, and it's going to update the one on R2. And now we've converged again, right? Does that make sense? Anybody, any questions on how this worked with the timeouts? Yeah.
If one of the router messes up with the TTL, doesn't that kind of break? Let's say if one of the routers sets the TTL to maybe like the router maybe let's say R3 is taken. Does it kind of break?
Well, so the TTL isn't, the TTL is set by the receiving router, right? So when it gets it, it sets it to, we've said it just, whenever it gets one, it sets it to 21. So.
The router itself cannot make changes in the TTL? Like you wouldn't make changes?
I mean, you could set your router to do it differently, yes. I mean, if for some attack or whatever, the way the specification works, if you want this to operate correctly, you don't do that. There's certainly any number of things you could do if you wanted to make things go wrong. Is that, yeah. Yeah.
So it looks like you have like a relative TTL
So I think what you're getting at is like, why don't you synchronize the TTLs between the routers? Yeah, I think we'd have to talk about this in more depth, but I mean, I think you're onto something. I think there's certainly, this is not the most efficient algorithm, and some of that comes just from having desynchronized clocks. Where are we time-wise? It's time. All right, well then that's it. I'll see you all next week. They're up. They're on Piazza. I will post them. Yeah, they're on Piazza. I will post them on the website. Yeah.